Professor Krishna Kumar did his engineering from University of Madras. Then he did his the Masters in Mechanical from Indian Institute of Science, Bangalore, and then did his PhD from IIT, Chennai. His core interest has been in non-linear and linear finite elements, biomedical engineering, and vehicle dynamics. And if you go through his profile, numerous publications, and morning he was telling that just one tire, he has 15 PhD students. So he's been working on, though we think tire is nothing, but lot of work has been done. Whatever we see today, much of that has been because of Professor Krishna Kumar's work. We have been working on a couple of projects with Professor Krishna Kumar. One was using our SN Reams data set, trying to do a fractal analysis and trying to correlate with cardiovascular diseases. We also tried the finite element analysis, trying to see the vitreous dynamics during vitrectomy. And more interestingly, we have also created a simulation background, trying to look at visual performance during driving. It's a small video which is one of our optometrists who is driving a real car. That's a real car in his MRF lab, and this is the virtual background from which he drives. A lot of scenarios which come, and we try to look at what is the visual performance. Basically, I'm looking at driving performance of diabetic macular edema and proliferative diabetic retinopathy. And I think at the end of this video, you will see the overall. So this is the screen and the real car. And he has put all EEGs, the visual trackers. So looking at driving performance in visually impaired is something which we are working with Professor Krishna Kumar now. Very warm welcome to Shankar Netralaya, and I would request Professor Krishna Kumar to talk to us about finite element analysis. Professor Krishna Kumar.
Thank you, Dr. Rajiv, for a very, very warm introduction. Thank you very much. In fact, I was discussing with Dr. Prema for the past 1 hour on keratoconus, cornea, and so on. So I have one of my students here who worked on tires, Dr. Srinivasan, who actually works in JK Tires and is working on a very important problem of tire failures, tire burst that takes place, how we can avoid it, and so on. And interestingly, all mechanisms, he was first slouching in his chair, thinking that I'm going to talk something else. Keratoconus and tire, what is going to be the connection between the two? And he was very relaxed. So as we started discussing, I could see his eyes, getting brightened, because the problem of keratoconus is exactly the problem of tire failures. I don't think anyone in this room would recognize that. It's exactly the same thing. All mechanisms that happen in keratoconus, all changes that happen. You are talking about IOP, we are talking about pneumatic pressure. There is no difference even in that. Structures are very similar, failures are very similar, and the unknowns are also very similar. There are so many unknowns. In fact, he did his PhD work for 6 years. Now it's 3 years he has been working to understand actually how tire fails, can we predict it, yet to find a solution. So there is so much of commonality in science. 2 days back, I was discussing with Dr. Ajan Ravichandran on chronic kidney disease. How we can determine chronic kidney disease, what exactly happens, what are the techniques that we can use, and so on. Again, very similar to many, many engineering problems in other fields like automotive engineering, like, for example, tire. So, if you look at it in an overall sense, the connections are amazing. And it's a joy to look at these connections. Though I'm at the far end of my career, working with people like Dr. Rajiv, I wish I can get some Kaya Kalpa to become younger. Okay, this is an amazing experience working with about half a dozen doctors on very interesting problems. Okay, coming back to this topic of finite element, I'm not going into the history of finite element, long history, so let's not get into that. But the formidable task for me now is to explain finite element, which is basically a mathematical technique to doctors. There are clinicians. A lot of them have joined in the net. So to explain this to the doctors. It is also difficult to explain it to the engineers. The first time I attended a lecture on finite element was, I was working in a company, and a professor from IIT-Madras, a pioneer in the field, came to give lectures. So the understanding was that he will give 30 lectures. The first lecture, there were 32 people. Second lecture, 15. Third lecture, I was the only guy sitting. The other guy who was sitting there was the organizer. His major worry is, I've ordered for 32 vadas, so what am I going to do with these vadas? So all of them disappeared. The first equation the professor wrote, all of them just scooted. So it is not a problem for doctors, it's a problem also for engineers. Many of them don't understand the mathematics that goes into finite element. So I don't think you are a unique lot, madam, especially you said we are allergic to mathematics. I think engineers are also, to be frank, allergic to mathematics. So it doesn't make any difference. So how do we now look at finite element, which is a numerical, if you really ask me a definition, it's a numerical method to solve partial differential equations. Please don't go away from the hall. Stay back. Partial differential equation, numerical methods, all of them look scary. But beyond all this, there is some simple way of understanding the stuff. Okay? I may not be very rigorous in putting this topic. If you want to be, if you really want to, my good friend Dr. Chandra Abraham already saw 5 or 6 lectures of mine in YouTube. He had already seen that. And when I told him finite element, he had seen it. Yes, if you are enthusiastic like him, go ahead, you can see my lectures, which are going to be very mathematical. But today I'm going to be, I'm not going to be 100% perfect, but I will explain things in a very simple fashion. Okay. Let's start with a very simple, I will have a few equations, but they'll all be very simple. So let's start with a very simple problem. Now, I'm going to ask you to find out what is the area of this figure. You don't know, obviously, the formula for this area. But you can easily find out the formula for the area of this figure by dividing this into figures or into geometries whose area all of you know. For example, you would say that, let me divide this into, say, a square, a rectangle, a triangle, a semicircle, and the whole as a circle. So the first thing what you do is, you look at it, you divide. So divide and conquer, not political, also in problem solving. So you divide this into a number of geometries which you know. Number 2, so one is discretize. This is what is the term I will use. Number 2, once I discretize them, then whenever I see that shape, I know what is the area, half b into h, pi r squared. In this case, half pi r squared, and so on. So I can calculate the area of each figure, or each geometry. The third step, what I'm going to do is to assemble them. What is assembly? I'm going to call this as A1, this is A2, let's say this is A3, A4, and A5. Then I'm going to write the total area to be A1 plus A2 minus A3 plus A4 plus A5. The last step is, I'm going to solve. What is meant by solving? I'm just going to add and subtract as I see this equation, and I get the total area. So what essentially I have done is, I don't know how to solve this complete area, but I know that if I divide this into number of geometries, whose areas I know already, and when I actually calculate that area, I'm not going to integrate. Actually, it comes out of integration and other things. I know it's pi r squared. Okay, I don't know, go into the derivations of it. I know its property. And then I put that and sum them up. This is the essence of finite elements. There are finite elements. Here, the property of that element which we are looking for is what we call as the area. The property which we will look for in some other place which we are going to see is a stiffness and other things, which I'll come to in a minute. Now, why is that finite element becomes important? Why is it that doctors should know finite elements? A later project actually comments from or the editorials written in very good journals like Annals of Thoracic Surgery. I'll come to that in a minute. But it is very well recognized now that finite element is a very important tool to look at physiology itself, to understand the physiology, to do what-if scenarios, to actually have a digital twin of the patient and look at how treatment can be done, how surgeries can be performed. I'm going to show the second half of my lecture, I'm going to show examples from neurosurgery where we can use finite element to actually plan surgeries. So it's a very vital tool of the future for clinicians. Not only understand the physiology, and maybe with time, not in the distant past, you can actually plan for treatment protocols. I will also discuss some of the interesting problems which we had, past 1 hour we've been talking about, and probably one of the most difficult problems also in physiology. So, what essentially you are looking for as doctors? There are two ways in which you can look at the problem. One, from a biological sense. The other is from a macro sense. So what do I mean by that? Suppose you want to look at the car. Car can be looked at from the material that it is made up of. Steel metallurgists are not car designers. You can, or you should know steel metallurgy. Okay, and steel metallurgy has a lot to do with car design itself, car manufacturing itself, but it is not the end of the car as per se. There are designers who look at a lot of other things in the car, okay, use steel as well, and then design the car, its geometry or shape, the thickness of the steel, how the seats should be arranged, how when you go over a bump you don't feel the bump, all those things. So there are car designers, they are car designers, okay, they use the steel, that's all. So this is exactly the distinction between what we call as engineering physiologists who understand physiology from a macro engineering perspective using the laws of physics, and I would own it as laws of engineering, and then understand the macro picture, go down the chain. Biology becomes extremely important at that stage, and then interact with the biologists to understand the changes and its implications and so on. So finite element is a very important tool from that sense to understand the macro behavior of organs and structures. So what is that macro behavior? Okay. In order to go, before we go to examples, we will go and look at the examples. We have to know what exactly is the technique. So that's what I'm going to do now. When we look at this physiology problem from an engineering perspective, the first question that any engineer would ask, okay, would be, what is the type of problem you're looking for? So what is it that you want to solve? For example, when we are looking at keratoconus, I'm sorry to take this example, it's very easy for me, just fresh in my mind. And so, if you look at keratoconus, Dr. Prema is looking at failure. What is the stress that results in failure? How does thinning takes place? And so on. So in other words, in many problems, there are two things that are important in many physiological problems, two things are important. One is what is called as deformation. The other is fluid flow and velocity, or I'll say just fluid flow. The problem can be static or dynamic. For example, if you look at blood flow from the heart to the rest of our body, it is a dynamic phenomenon. Actually, there is a wave that is created, and the wave travels, gets reflected, and comes back. So it's a dynamic problem. Or it can just be a static problem where there is no variation of load with respect to time. But many of the problems in physiology are problems where the load changes with time. That's the first thing. So the second thing, these problems where deformations are involved, where the forces that are applied can change with respect to time or not, or what engineers call as solid mechanics problems. So it's a solid mechanics problem. For example, if I want to find out the stresses in the cornea, then it becomes a solid mechanics problem. Given an IOP, what is the stress? This is a question. Stress is a derived quantity from deformation. First, I want to find out how much it is deforming. And the deformation gives rise to strains. Strains give rise to stress. So there's a connection between all three. So a fundamental quantity which I would like to get is deformation from the force. In this case, IOP. In other, say for example, if you're looking at arteries, then it is the blood flow, pressure, and what is its we'll see that examples, and on the body and so on. So these are solid mechanics problems. Solid mechanics problems can be are based on deformation, or in other words, the fundamental quantity in solid mechanics problems are deformation. Now you may come and tell me, look, it is not that all problems, forces are well known. Here IOP, I can give you a number, but if it's a blood flow, I don't even know the pressures that are acting at various parts of the body. I don't even know it. So in other words, you would say that I am not interested only in deformation, but I am also interested in, say, velocity of some fluid flow. I've used Doppler, I've used this, I used that. So what are you trying to do? You're looking at velocities, accelerations, and so on. So the second problem that is of interest to us, to the physiologists, is fluid flow problems. So I would say fluid flow problems. Then the third thing you would come and tell me is that, look, I'm not going to look at fluid flow separately. I'm going to combine fluid flow with solid mechanics. So I'm going to look at what is the effect of fluid flow on stresses and deformations and so on. I won't have a single number. I want to know, say for example, I want to look at organ perfusion pressure from fluid flow, and then what happens, say for example, how does the flow takes place in kidney, and what is the effect of deformations and so on. So you would say that I'm looking at vasodilatation, and what is its effect on the heart function and so on. So in other words, you're not going to look at, in many problems, you're not going to look at fluid flow separately. So you're going to combine that with solid mechanics, and you're going to say that I'm going to look at fluid structure interaction problems. So the third problem is fluid structure interaction. You're not happy with these three things. There is heat transfer. There are many procedures. Like I was talking to other day with Dr. Suresh of Mediscan, who's an excellent ultrasound specialist. He was looking at some ablative techniques in fetal surgeries. He wanted to know whether I can calculate the temperatures because I wanted to know whether the ablation would have an effect on the damage and so on. So there are a number of heat transfer problems that is also interested, or that's also very important in physiology. So the fourth problem that you would look at is heat transfer problems. Then there's a big field of electrophysiology. You look at the ECG as a tool to determine the performance of the heart, but then the electrophysiology problems are again controlled or again explained by means of mathematics or characterized by mathematics. So there are equations which actually govern that. I'm not going to write the equation now, but that govern it. So I would say that fifth problem is some electrophysiology problem. So, in other words, this set of problems, okay, for us, this is from a doctor, you would say, from a clinician, you would say these are the problems. For us engineers, each one of them are governed by a set of governing differential equations. I would say that, oh, you're talking about solid mechanics problem. I would say, yes, this is a partial differential equation, equilibrium equation. It can be, depending upon the problem, it can be elliptic, it can be all those kind of things. So for us, every problem is defined by means of a set of equations. It can be, governed by the laws of science. It is conservation of mass, conservation of momentum. We give different names to it. We'll call this as Navier-Stokes equation and all that. So the fundamental laws which govern many, many other physical phenomena happening all over the world are the ones which control also what's happening in our body. So for me, ultimately it reduces to the laws of physics or mathematical equations. So I will put all of them in one basket and say that this is my problem basket. And for me, it's an equation. For you, it is a physics which you see every day. So you can come and tell me that I want to determine stress in this keratoconus, then I'll pick up the first problem and say, okay, you're looking at solid mechanics problems. So why is this important? Because I already have solutions to it. I already have solutions which has been worked out, and in a broad sense, that's what we're going to see now. So in each of these parameters, in each of these, I have parameters or I have variables to define the process. For example, in solid mechanics, as I said, it is the displacement, which I would call as deformation. In fluid mechanics, I would say it is the velocity of fluid. In fluid structure interaction, it is the pressure which crosses from the fluid to the solid. In heat transfer, it is the temperature. Electrophysiology, it is the voltage, and so on. So there are variables which actually you measure and which actually gets into the equation as well. Okay, so there's a good connection between them, and hence my tire is no different from cornea, because they are fundamentally governed by equations which actually percolate across disciplines. So what I use in my tires to solve the problem is what you can use to solve physiology problem. There's no difference between the two. I face this problem all the time. What? You're doing some tire design? Yes, tire design. Our friend here, Srinivasan, the first thing he noticed is, sir, did you look at Dr. Rajiv Raman's car? He has put a JK tire. That's what it comes to him naturally because he works for JK tire. So, but at the same time, the laws actually, so doctors use JK tires, so you will be happy with it. So, so the laws govern the same, and so I have some techniques to solve them. That's the first thing. But then, the life for you is much more difficult than us, because the next comes, okay, that's the first thing. How does the material behave? How does cornea behave? How does the arteries behave? How does the bone of all things, totally different, how does that behave as a material? So I have to characterize material, because all of us immediately would say, hey, I apply a force on steel is different from when I apply the force on rubber, the deformations are different, and all those kind of things. So in other words, close to the laws that govern the variables, we have a set of different laws which govern material behavior. These laws, interestingly, the law is exactly the same what I use in rubber to most of the the laws that are used for most of the organs in the body. They're exactly the same, because both of them have long chain molecules and blah blah blah. So this kind of laws which actually connect different quantities, okay, whether it is a body or tires and so on, for example, connecting strain and stress, are called as constitutive laws. That is my next basket. That's my next basket. Now, just to pick an analogy with the area which I have said, I have just talked about, where I divided this into a number of areas, the key factor there is somehow in my brain I have stored that, hey, this is a triangle and I know that area of that triangle. So that is why I actually divided it the way I divided that figure. In other words, I know it. I wouldn't have done it anywhere else. So if I go back to that area, I'm not going to divide it, say, like that, because this area I will never be able to calculate. So there are some fundamental knowledge that is available to me, and with that knowledge, I said, okay, I'm going to divide it. This is exactly what we are going to do here. We have a set of laws and set of behavior. And what I'm essentially going to do is to connect them. That's all. So let's look at what is constitutive laws. So if I now look at steel, obviously we know that the steel is different from the skin, from the muscle, from the bone, and so on. But all of us would say that, hey, looks, when I take out my hand, I push it, I take out of my hand, the shape is regained back, and so this is also elastic, steel is also elastic. So you can connect, at the same time there are differences as well. So constitutive laws are the ones which makes this difference possible. So there is what is called as linear elastic. So that's a first constitutive law. So linear elastic. So there are a set of materials in the outside world which are governed by linear elastic. Steel is one of them. So there is a relationship between stress and strain. I hope all of you are familiar with stress and strain, or else I can explain that. Better explain once. Okay. Now, right. So I have, say, for example, a bar, which is whose radius or the diameter, is a circular bar, is high. And then there's a thin bar. Okay? And I'm going to apply force to this. I'm going to hang. So someone is hanging, immediately you would say, hey, that's very thin, be careful, it's going to break. If it's thick, you're not very worried. Now, what is this thick and thin? You somehow feel that the force that you are applying may be the same. You are the one who's going to, hold it, but you know that that force and that thickness has an effect. Force in the area has an effect. So long ago when Cauchy did experiments, he found that if this force is now normalized with area and called it as stress, he found that the failure of these two bars, whose areas are different, are governed by sigma, which is called as the stress. So it doesn't matter if area is A here, say 5, if this withstands, or if this you apply a force F is equal to 5, and then sigma is equal to 1, it fails. Then if the area of this broader one is say 20, then you can apply a force of 20, say 20 Newton or whatever it is. And then this 20 can withstand a force of 20 Newtons. And so the ratio is 1. So in other words, he found that normalizing by the area is a very good measure of what's happening to this bar. Either failure, becomes plastic, whatever it is, it's a good measure. And call this as stress. The other thing he did was to see how much elongation that takes place. So this elongates. So for example, if let's say the area is the same, I have 2 bars. Okay. He found that the elongation due to this, now we'll call this a stress now. We know what is stress. So sigma, okay, is not the same. But he found that when there is an elongation, okay, which is say D, that's the elongation. Let's say that this length is L. And he called a strain D by L. Okay. He found that this quantity D by L for a given stress for the same material is the same. So in other words, if the length is high, D is high. Okay, so the strains are the same. Okay, so in other words, he found that stress and the strain are related by a quantity called E. Unfortunately, most clinicians confuse E with stiffness. We say E is the Young's modulus because stiffness for all of us is the relationship between displacement D and the force F. So if you now, I'm going to do very simple mathematics. There's nothing. Today kids learn this in their womb, may not even be born. So that's the mathematics, because I'm afraid when I talk about differentiation, I did this in 6th standard. This is what kids say. I'm a bit worried to talk about mathematics to high school kids. Things have changed considerably. What has also changed is the noise of the chalk, which Chandran Abraham very beautifully told me, which is a lovely music to the ears in a class when we teach and we write in the blackboard. Okay, unfortunately, we have lost that as well. But nevertheless, so I'm going to just do a small. So F by A is sigma, I said. That is equal to E into epsilon. Epsilon is the strain, and so I will put that as dl. I'm just going to rearrange it. I'm going to take A to the other side. And so I will write this as F is equal to AE by L into D. This is a very important thing. Why am I saying this is important? Now, just to pick an analogy, let's say that I have a spring. Okay, just a spring. I'm going to apply a force to it. If the deformation of the spring is small, you would immediately say that it is stiff spring. If it is going to be, as soon as I pull it, it's going to just come out with me, you will say that, it's very compliant, stiffness is very low. So you related that force with that displacement. So force divided by the displacement is the stiffness. So if you look at this equation, F is equal to AE by L into D, obviously force relationship to D comes up with AE by L. So the stiffness of that rod K is actually AE by L. Why is this important? This is important in every walk of life. So E is only one quantity that enters in this equation. You can have a thick rubber block and a thin or less stiff steel sheet. Steel, we know, is very, very stiff. Rubber is very compliant. But I can make a bar such that rubber is stiff, steel is not stiff. So any stiffness is a combination of the material property, which in this case is E. I'm introducing that now. That material property E, as well as the geometry A and L. So it is a combination of these two which gives you the stiffness. So geometry becomes very important. Okay. So that's exactly what body does. Form follows function. So you do pumping the iron, form follows function, so you develop the all important muscles. This is what happens everywhere in the body. This is form follows function. The whole idea is that body starts reacting to stress. There are sensors in the body which reacts to stress. So this is a very important concept of stress, strain, stiffness. Okay. Please note that that is different from strength. Strength is where it's going to fail, the stress at which it's going to fail. So stress is different, strength is different, strain is different, stiffness is different. This we have to understand it very clearly because people usually use it loosely, but they're all very different quantities. Okay. Now, let's come back to this. So if there is a rod like this, now that I know the formula, if I ask you if I am going to apply a force F, okay, if the area of this is A and is made up of steel whose E is some value 2.1 10 to the power of 5 and so on. So I know the L, can you tell me what is the stress, what is the strain? You can very easily calculate it. Okay, because you now know AE by L is the stiffness. Okay, so in other words, you see this in another flow. Deformation is the fundamental quantity. Well, as soon as I apply the load, there's going to be deformation. Deformation gives rise to strain. Okay, so there is I calculate it. Then the force also gives rise to stress, or I can calculate stress from strain through the E value. So they are all related. So the first thing is that what I have just explained is linear elastic, very simple case. Unfortunately, that is, in other words, stress is proportional to strain and the proportional quantity is E, very simple to understand. Unfortunately, nothing in physiology, except maybe the bone to a certain extent, is so very nicely defined property. It's not linear elastic. It becomes extremely complex. And most of the pathological conditions changes this material property. And so we have to go beyond linear elastic, and there lies the difficulty of understanding. We'll not go into too much of details. So in other words, if I have a spring where sigma, that stress is proportional to strain, E, one value. So if I now draw a graph, it's a very simple graph between the strain and the stress, it is just a straight line, the slope of which is E, very simple. But if I now take out cornea and do exactly the same thing, if I now apply force, okay, very different things happen. If I now plot the stress and strain, the curve is no more going to be a straight line. The curve is going to be like that. In other words, we say that the stress, the strain and the stress are not related by a linear case, but is non-linear. So in fact, all the ophthalmologists would be very happy to hear that it's so difficult to do all this analysis in the eye. Because every part of the eye behaves in a non-linear fashion. And the non-linearity, as it changes, the pathological, the conditions induce it to change the properties. So this is called non-linear. So I have linear elastic, I have non-linear elastic. People call this with different names. In non-linear elastic itself, there are various models. That's okay, we're not going to go into the details. That's the third is, as you were telling, madam, there is viscoelastic. So essentially, if you want to understand the material behavior, you can very simply understand by three simple stuffs. One is a spring. Another is a dashboard, the shock absorbers that you see in your car. And the third is friction. You can combine these three to understand the material behavior. If it is just a spring, only the stiffness, then that's the quantity which gives you the property. It can be linear or it can be non-linear. Purists call this non-linear as hyperelastic, governed by certain laws of thermodynamics. It's not our concern right now. So it can be linear or non-linear. It sometimes hardens. Now, we have another thing called the viscous dashboard, which actually responds to velocities. So the combining these two is viscoelastic. So I can look at a material behavior, for example, cornea we were talking about, is a combination of the spring and a dashboard. So it is viscoelastic. In other words, it has the property of a fluid and a property of a solid. So it's a combination. That's why you say 99% water, that has to manifest somewhere, and it manifests as this dashboard. And with disease, the viscoelastic properties or the viscous part of it keeps changing. People say that it becomes fibrous, which means that I'm going to lose out of the fluid and the solid part. I'm going to lose out one of them. As I lose out one of them, I get into trouble. So combining these two, okay, I can create models which would mimic the actual organs. For example, I can connect it like this, and this is called as a Kelvin-White model. For example, we were talking the other day to the nephrologist, Dr. Rajan Ravichandran. So the kidney is actually modeled like this. The viscous part of the kidney is modeled like this. This is called Kelvin-White model. Or sometimes you can say that I can connect these two like this. This is Maxwell model. I can make it more and more difficult. So why am I doing this? Because this would actually give me how the material or that part of the body behaves. So the third one is viscoelastic. So for our purposes, these three models are sufficient to look at the material behavior. So this is the second basket. Okay. The third basket that I would look at is what is called as the structural behavior. This is a very difficult basket to understand for non-engineers and even for engineers. Not many people, when I ask questions, they answer it correctly. Okay, so I would give you 2 or 3 examples, okay, to make you understand what we mean by structural behavior. Suppose I have the same bar. I'm going to keep it like this. The bar, it's just a bar, which is, what does this mean? It means that I'm fixed it. I have fixed, this is the bar, I have attached it, it's fixed. And then now I'm going to apply load at this one end. I'm applying the load here. So this is called as a bar. Bar is actually a technical term. It's not English. It's a technical term. Bar means that I am applying the load along the axis, and the displacements or deformation of the bar is going to be along the axis. So this is what is called as a bar. But if I had applied the load in this direction, suppose I'd applied the load in this direction, then the same bar would behave in a different fashion. Everything being the same would behave in a different fashion. All of us know this, it will start bending like that. So there is a bending behavior, it bends. The previous case it did not bend, it just elongated. In this case now it starts bending. So the bending behavior in engineering terms is called as a beam. Then I have thick solids, thin solids, and so on. So each one of them have a structural behavior. This is what is called as a structural behavior. If you would have noticed, it's a combination of geometry and load. Suppose I have something like this. You would call this as a plate. In engineering terminology, plate simply means that the loads are acting like this and plate will start bending like that. This is called as a plate. So this is a structural behavior for me. For you, it's an English term for a plate. So it's a structural behavior. Plate means I'm going to apply loads in this fashion. Then I have a shell, cornea. It's actually what is called as a shell behavior. The way the load that you are acting, that you are applying, and the load that's applied, say, to a cornea through the IOP, their behaviors are different. The loads here in this case, in the cornea, is taken through not only a deformation, but also through loads that are acting along its plane, like this. So, this is called as the shell behavior. This is called as the plate. So, the English terms that you use also has an engineering meaning when you look at how they react to loads. So I have bar, we have seen bar, we have seen beam, we have seen shell, we have seen plate, and everything in this world is 3 dimensions. So I would say it's a 3-dimensional behavior. Why are we interested in these kind of things? Because the type of equations that it governs is different for us. You need not be worried about the 4th order differential equation which the beam behavior is captured. Forget about it. It's like calculating the area. I never knew how pi r squared has come, but I know it's pi r squared. So don't worry about that. But nevertheless, you should understand that these behaviors, from a very physical sense, they are different. Leave it to us to do that part, but this becomes very important. So 3D, and I can assure you that many engineers also do not know this. So the last basket which I'm going to look at is what is called as the load and boundary condition basket. So when we were discussing again, you want to look at cornea, how is it attached? When I now want to model, should I model the sclera also? What happens at the interface? If I look at contacts in joints, say for example my knee joint, how does actually the force gets transmitted? Okay, what is the force? How does it get transmitted? There is a contact between 2 bones or between 2 parts in an organ and so on. So what is the force? How does this force, actually there is an action and reaction for everything. There is an action which may come from IOP. There is a reaction which is taken, say for example, where the cornea is fixed, maybe it goes to sclera and so on. So there's an action-reaction components. So that is the force that is applied, and there is a reaction that is taken for the force. If there is no reaction, suppose I'm not going to hold this pen, I'm going to apply a force like this. Now my left hand is going to feel the force that I'm applying. So there's an action by my right hand, and that action is felt in my left hand. Suppose I leave it, I pull it, look at that. The pen has gone now. It now has traveled with actually an acceleration. So it's either F is equal to ma, which is force that's happening, or I'm going to have a reaction that's here. Sometimes it's a combination of these things. So the last basket is, what is the pressure, or what is the force, how is that force taken, the complete physics of the organ. That has to be understood, because that's fundamental, that's biomechanics, that is fundamental to further analysis. So these are the 4 baskets that defines a problem. So any problem that you take, I will pick up one from the basket or 1 or 2 from the basket, okay, assemble them together and define, hey, this is the problem I want to solve. So these baskets are very important for physicians. Further down, after this basket, it doesn't matter. It's all our game. Already people have worked out, there are softwares and so on. So there are very many problems where the combinations, I'll give you some examples as we go on. I can pick this up and tell you. Sometimes problems become difficult because I have to pick more than one from this basket. We will also see these problems. Sometimes the boundary conditions are based on contact between 2 bodies. That also has to be taken into account, and so on. So fundamentally, the problems are defined by these 4 baskets and forms the basis for finite elements. Okay, I'll stop here for a minute. If there are any questions, I'll take, because I think I covered maybe about 8 to 10 hours of lecture on finite elements. Matter of about 30 minutes. So I'll be very glad to answer any of your questions. I'm always worried when questions are not asked. I assume that they're all gone above the head. I don't want to assume that I'm a great teacher, that I've taught so well that, every part of what I said is understood by people. I'm a bit skeptical about it. Yeah, yes.
It's not a direct question, rather trying to.
Yes.
With respect to cornea.
Yes. Very good question, and that's what I'm going to do with a number of examples in the second step. But I would say, for instance, cornea, so I would say that, let's say I know the IOP, so I would say, okay, I'm going to do a solid mechanics problem. So from the first basket, I will take solid mechanics problems. So from the second basket, okay, what is that I'm going to look at? It is, what's the material? The material is nonlinear, elastic. Should I include viscoelastic? So yes, it may be viscous. Then I'm going to go into the details of what is this nonlinear elastic. Okay? Then it becomes more complex, anisotropic nonlinear elastic. Let's say, for the time being, right now, say I'm from the second basket, I'm going to pick up the material to be nonlinear elastic. So I have 2 things. From the third basket, I'm going to look at cornea, and I want to know what I'm interested in. So I would choose the behavior, for example, as a shell behavior, something. So from the third basket, I can pick shell, or you are very experienced, you can pick 3D, 3-dimensional. So 1, 2, 3. Then I'm going to, the boundary conditions are not simple. I will explain that in the next set. So I'm going to take how actually this is fixed. Action, reaction. Action is IOP, reaction. Suppose I want to find out how, when you put your finger and squeeze your eye, what is the force? Very important. So there, this is the action, and the reactions are taken somewhere else. So I understand that. So the fourth is, now all these things combined together is the problem. So what is that I'm interested in? Hey, I've given you these 4. Okay, I know the force. I've given you where it is going to take the reaction point. I know how the material behaves. I know it is just a solid mechanics problem, and I have given you that it is a behavior like shell. Now tell me, what is the strain? That is what engineering gives you back. Okay, if you do all these things, This is the stress in your cornea. This is the thickness change in your cornea. This is the strain in your cornea. So that is what I give you back from finite elements. Is that clear? Yes, sir. What is the term? Hyperelastic. Okay. It is usually 4 hours of lecture. Okay. But I'll explain that. The problem is my students here, we earn our living by hyperelasticity. So the first thing that, so that's why we're very excited when you ask that question. So the first thing is that hyperelastic doesn't mean that it is hyper, lots, nothing to do with it. Nothing to do with it. So it is the definition of elastic. It's a very good question because every part of our body is governed by hyperelastic. I'm sure you would have seen this in every paper in cornea, right? Every paper says, let us say this is hyperelastic. I know that's why the question came. So let's look at hyperelastic. First of all, doesn't mean it is elastic. Okay. Now, as I told you, there are 2 ways in which broadly a material can behave. One is, if this is stress, this is strain, linear. Many bones you can model it like this. On the other hand, the material may not behave like this, but behave like that. It can harden later, or it can soften later, and so on. So this is non-linear. Now, when I want to characterize it, I can say, okay, this is stress is proportional to strain, and so E. So I can go and just fit one curve for this. It can be, say, cubic or combination of them. Today, with machine learning, it's always curve fitting. And if you give this to any machine learning data analyst, any person immediately say, hey, what's the problem? I can easily fit a curve to this. Unfortunately, nature doesn't work like that. Unfortunately, it is not the curve fitting that actually satisfies laws of thermodynamics. Okay, so there is a fundamental property of the material called strain energy. Okay, there's a fundamental property of the material called strain energy. What is strain energy? A strain that you apply to a body. Okay, how is it stored in the body? That's what, for example, the very famous example is the pole vault, or people use what is stored to look at elastic recoil. Okay, so when you press something, leave it, bumps back again, because the strain energy that is stored as you are deforming, when you remove your force, springs back. So that there is a strain energy that is stored. Okay. Usually the strain energy in all your journal papers would be called as W. If you see every paper, it's W. Well understood. So when I now look at stress and strain, the relationship can be direct between stress and strain as curve fitting. Okay. But since it doesn't satisfy certain laws, and especially laws of thermodynamics, we say that what is elasticity is not what a common man says, that it is when I leave the force, it comes back to the original position. It is not enough. But we define an elastic material as one which has what is called strain energy, okay, when you load. And that the relationship between the stress and the strain comes through the quantity called strain energy. In fact, if you don't mind, in one mathematical equation, sigma is equal to what is called as the variation of strain energy with respect to strain. So, in other words, we postulate the existence of what is called strain energy in the body, and the strain energy controls the connection between stress and strain. So, in beginning engineering courses, they would say that strain energy is nothing but the area under that curve. If you ask any engineer, that's all he would say. He won't know what is hyperelasticity. I can assure you that. Okay, so I can assure you that no one would say that. But for all biological tissues, we define the material to be one which has an inherent property called strain energy, which is responsible for it to store whatever you are giving from externally. And when you release that force, for example, IOP, it position changes because there is a take back of that strain energy. So the connection between these two, this is the one which defines what is called as the relationship between stress and strain. Now, again, if you look at papers, they would immediately say W is modeled as Yo model. In fact, most of your keratoconus papers, you would have seen that it's a Yo model, Ogden model, Holzapfel HGO model, and so on. So there are a number of, for example, for tires, we use exactly the same thing. We use Yo model, and that's what. So Yo models are pre-existing models that define the way actually the material stores energy. It's an equation. It's a pre-existing model. Okay. More than this, the equations become complex. So I have to go into tensorial notations and so on. I'll just say that these equations are the ones which define how material behaves. Fortunately for us, you need not worry about that at all, because there are enough softwares which would take care of it. You have to know that hyperelastic means it is nonlinear elastic, defined by means of a strain energy. That strain energy is defined by means of an equation. That equation is Yo, Ogden, blah, blah, blah. Okay? Yeah. See, we also have to survive to confuse you, or else it becomes very simple. Usual sentences, பேசுறது ஒண்ணுமே புரியல சார், ஃபர்ஸ்ட் கிளாஸாக பேசினார், that's the standard statement in, at least in this part of the world. So we also have to confuse you a bit, and that's why we use, or else papers don't get accepted. As simple as that. Okay. Any other question? Yeah. So having got this and having defined that the most fundamental quantity here is deformation. Okay, and from deformation derives a lot of quantities or velocities and so on. So let us see how we can capture this. So what is the problem with this whole thing? So suppose I have a spring. That 3 lines simply means that I am holding the spring at one end. There's a spring. And I apply a force F. As soon as I apply a force F, there is a delta or D. There is a deformation. And then the K, the stiffness, is F by D. Okay, fine. This is very simple to understand. So we've been talking, for example, for a long time about this body is stiff. Okay, English statement. It's a very stiff body. So palpation is one thing which every doctor does, and say there is a stiff lesion, something like that. So what is stiff? What is stiffness now? So let's say that that's the lesion you're talking about. You say it's stiff. So what's stiff? Because here I have very mathematically, very clearly defined what is stiffness. So intuitively you may say, I'm applying a force and it is going to deform. And so if it doesn't deform much, I would say it is stiff. If it deforms a lot, you would say it is not stiff. Right. Now, that may be very problematic definition. Because if I now apply a force at this place, okay, as you were just telling in cornea, there is at one place this thinning, the deformations are large, okay, And you may say that stiffness is not high, at another place it may be low, and so on. So the stiffness definition becomes very difficult. If you look at this, what I have just drawn, there is a force, there's a displacement at that point which you actually measure. In any body, lesion, whatever it is, there are infinite number of points. There are infinite number of points. At infinite number of places you can apply force. So, suppose I apply a force F here, okay, I measure some displacement here. Is it also stiffness? So this also see, because when I apply, the body may deform like this, say for example. So why should I apply, or why should I measure here alone? I can measure it here, I can measure it here, I can measure it at millions of places, tending towards infinity. So what is this force? What is this displacement where? Why should I apply the force here? Maybe if I apply the force here, still can I get the stiffness? So I can apply force at any point in this body. I can get displacement at any point in the body. With the result, I'm totally confused. There are infinite numbers of them. So if I say this point, I will apply force. Why not this point? There's a very point close to it. As you go down and down and down, we call this as a continuum. There are infinite number of points. So if I now tell you that this lesion stiffness are infinity numbers, you're totally confused. What is this? I just applied a force and I know it is stiff. Now you're telling me that there are infinite number of values for this. Yes, that's the truth. Because we are now entering into numbers. We are looking at a quantitative technique, not qualitative. So I'm looking at quantitative technique. So I'm now going to say that I have to be more specific. The first thing is that I have to remove this infinite numbers. I don't know what is infinity. Maybe Ramanujan knew what is infinity. None of us know what is infinity. Infinity plus 1 is infinity. I'm totally confused. So I can't deal with infinity. I have, whatever be the big number, I have to reduce it to a number. 1 followed by 20 zeros. Still I understand that than infinity. So what I'm going to do is to divide this complex object, okay, or choose some points in this complex objects. So there are points already here, so I'm going to choose a number of points. Here. It can be 100, 1000, 10,000, 10 to the power of 6, whatever it is. As I said, I know numbers. So I'm going to choose these numbers. So I'm going to, these are my guys. So I have chosen them. They are the bosses. I have not chosen, say for example, this point here. I have not chosen it. Okay? But that guy there also is going to deform. Okay? So when I look at this material, points which are lying in this body, I have some points for which I have a vested interest, and chosen them, my chosen guys. And there are points which I have left out. So when I now apply a load on this body, say F, these blue guys are going to deform, and the red guys are also going to deform. Okay? Now I can't leave that red guys out because they are a part of this body. So what do? I say that I give freedom to my blue guys. Okay? They are the satraps of regions. I give freedom to them. Okay? So I'm going to say that all other guys, this red guys, are going to behave as dictated by the blue guys. What does it mean? So what I'm going to do is, I'm going to join and create regions. I'm going to join and create regions. These are called as elements. So I'm going to join them and create regions. And so on. And I'm going to say that all the blue guys whom I have chosen are at the corner of these figures, these rectangles and triangles. And they have the full freedom to behave to the applied force. Oh, then what happens to the rest of them? They are all my slaves. These guys only have degrees of freedom. So the red guy sitting here, is in a region. That is the region. So he is going to behave. He has a boss. He has 4 bosses, unfortunately, in fact. Difficult to listen to one boss, but here we have 4 bosses. So I'll just take that region out. That's out. So I have, these are the 4 guys, and this guy is sitting here. So this red guy's bosses are these 4 chaps. So he has to behave dictated by these 4 guys. Now how is he going to behave? Very simple. There are 4 guys. One sitting close to you, one in your regional center, one in Delhi, and so on. So the best thing to do is, under these circumstances, to listen to the boss who is very close to you. Okay, he's going to look at you. So if this guy is going to get, say, displaced by U1, this guy by U2, say for example 2 mm, 3 mm, 4 mm, 5 mm. These are the displacement in this direction. Then this red chap is going to listen to them and interpolate them. So if the red chap is very, very close to number 1 guy, he would listen a lot more to 1, almost 90% of it from 1, lot less to this 4 who's far away. So this kind of behavior, where the position determines his allegiance, is called as the interpolation. So we are going to interpolate the displacements in terms of where it sits. So there is an interpolation. So now wherever you choose, if you choose a point right at the center, then his displacement would be the average of displacements of the 4 blue guys. If the blue guy the red guy sits exactly at the blue point, very, 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 very close to it, then his behavior is totally controlled by that point, and so on. So now I have solved this problem. I have infinity, I have brought it down to a finite number, and then number 2 is that I have other guys whom I have not chosen, I have told them how to behave, solve the problem. Now, with these 2, let me look at this expression here. K into D is equal to F. This is the equation for stiffness. And K, remember, came from my geometry as well as material behavior. AE by L. Right. So now that I have chosen some bosses, and let me say that I have the liberty to apply forces at the chosen points. Let's say there are 300 of them, 300 blue guys. So I can apply loads at 300 points, which means that F is now in the first point, F2 in the second point, F3 in the third point, F4 in the fourth point, and F in the 300th point. So this is actually a column of numbers, F. And I already said that for this F, the behavior is monitored only at the blue points. They have the freedom to move for this force. So D is also D1, D2 up to D300. Okay. We are now looking at D as the displacement in one direction. If it is in 3 direction, 300 multiplied by 3. Let's not worry about that first. Okay. Now, then what is K? So the K is sitting here. K is now no more one number, but a big, what we call as matrix. It's a matrix. Okay, so there are K, we call this as K11, K12, and so on, multiplied by D1, D2, and so on, which would give you F. Don't worry if you don't understand. But only thing you have to understand is that K is no more one number, but a lot of numbers. That's all. So if I apply a load here, what is the displacement there? The connection between them would give me 1K in this matrix, and so on. So this is K. So now I have now divided them into finite elements. And the force and the displacement are connected by what is called as the stiffness matrix. Now, why matrix? Because there are number of K values. It's not one value. Matrix. Okay. Now, in this, for example, I was just talking about sclera, then fixing the sclera at a particular point. It has to take the load. That is called boundary condition. So I am going to impose the boundary condition here. Say D35, D36. Okay. That is, in other words, I have numbered all these blue guys from 1 to 300. The 35th guy and the 36th guy are fixed. That also I am telling. That's called as the boundary condition. And then I'm going to apply the load at F1, F5, F20, and so on. At 1.1, point number 5, point number 20, I'm going to apply the force. Now, these are known things. With these known things, I can solve it. Forget about how I'm going to solve it, but I will solve it and find out the displacement at all other points. Done. Similar to that good old spring, when I apply a force, I had to find out this D, and I did this using K, the stiffness of the spring, and said K into D is equal to F. One number, I found out what is the displacement. Here, now, if I have a body like that, and if I now apply a force at this point, and you want what is the displacement at this place, I can find out now that as well. So I have divided an infinite number of points into finite number of points. The finite number of points have given rise to a finite number of regions, and these regions are called as elements. So that is why it is finite elements. So the key here is what is K. So the K comes from this basket. Now you would understand from where, the K comes from this basket. Remember that the K was A, E by L, considering it to be a bar. So the K matrix comes from picking up what did I do? I picked up linear elastic, so it was E. I picked up a bar as my structural behavior. So I had that A, E by L. I fixed at one place displacement boundary condition. I fixed it, D is equal to 0. I applied load at the end. So precisely that is what would give rise to my K value here. So I'm going to pick up one from this basket, one from this basket, one from this basket, and then I'm going to assemble them together, and that is what engineering gives you. The K matrix is what engineering calculations give you. Once you know this, you can calculate the displacements. When you know this displacement, there are enough relationships to calculate strain. I'll go back to that basket about hyperelastic material and get the stress. So displacement gives rise to strain, strain gives rise to stress. And I solve this problem. So every problem is a question of properly choosing from this basket, putting them together, and calculating K and solving it. Fortunately, we have a number of softwares to do this. And so we'll see in the next part of the lecture quickly some examples. I'll stop here for any questions. Yeah, please.
Very interesting explanation, made very easy. So I wanted to ask that in your
model here where you've put the red dot. So is there, from my understanding, is there an assumption that the red point will behave like the blue points always? Is it
No,
in the
red point is controlled by the blue points.
So this assumption does not
It
be
is called, yeah,
violated.
it's an interpolation. You know, I can, let me explain that. So for example, I have, just take 2 points. Just take 2 points. And I change the color here, sorry. So let me not confuse you with the, so let me do the same thing. So I have a blue point here and a blue point here. Let's say it's one dimension, only one line. And I have a line like this. Okay? Now I choose a red point right in the middle. Okay? Now there is a displacement of this as d1. There's a displacement of the second point as d2. It's right in the middle, so the displacement here is d1 plus d2 by 2. This is called as an interpolation function. It's a linear interpolation, an assumption.
Assumption, okay.
I can have, but for 2 points, I can have only linear. Suppose I have 3 blue points in one line. Okay, this is a part of that, the chosen elements. Suppose I have an element like this, where I have more number of points, blue points, and I define an element using more number of points. Then it need not be linear. It can be quadratic, okay, and so on. So these are called higher order elements,
Okay.
right?
And does the area of the point making the pressure or on that area make a difference on those points?
Yes. So these points are the ones ultimately where I'm applying the force. Okay. Say for example, that's a body. Okay. I am applying a force in this place. This is called pressure. The pressure is now converted into force at, say, these 2 points, and then they are applied like this. So they are converted into a force into these points. Is that clear? So the chosen points are the ones which matter to me, and that's where I'm going to give the force. And the chosen points are the ones where I'm going to measure displacements.
So will you choose a size for that point? Size or an area for that point? That's what I want to ask.
Okay. Very good question. We don't have time to, that's a big topic. Yes, size is important. Number of these nodes, they are called nodes. These blue points are called nodes. They are important. Okay. To answer your question in a very simple fashion, suppose along a direction, my displacement, this is the direction. Let's say this direction is, if you don't understand it, tell me, this is the direction x. Okay. Now, along this direction, the displacement varies like that. Okay. In a body, like for example, I'm applying the force here, and I want to know how displacement takes place along that line. This line is this line. So in other words, the displacement may be like this. If the displacement is very sharp, okay, that is, the curvature is very sharp, then I will choose more number of blue points to define. If the displacement is a straight line, okay, then I will choose only a few points. Okay, that would define the displacement.
Thank you.
So the displacement depends upon, the nodes depends upon the displacement.
Thank you so much.
Figure, yeah. Yes, please. Is it okay if it takes some time? Another, doesn't matter? Sorry.
When you speak about displacement, we are assuming it is between two structures of a known density or of a known nature. But within the eye or within the body, you may have a fluid of a different viscosity, you may have a solid there. So will that have to be changed?
So suppose I have a whatever, I'm just randomly drawing, whatever it is.
Yes.
So your question is, will the displacement be different at different points of the body?
Because the force may need to be different, right? If you're doing between two solid elements or one, if you're displacing within two solid elements or if you're displacing between a solid and a liquid.
Yes. So, so let's take an artery, maybe an example, or you give me any other example. We will.
Yeah, like you keep talking about the cornea.
Yeah.
So if you look at the cornea as a whole, you're looking between the air and between the
Yes.
aqueous humor.
Yes.
But if you're looking within the cornea,
Yeah.
or similarly, if you're looking at the retina, you're looking between the vitreous or you're looking between the choroid. But if you're looking within the retina, which has 10 different layers, and you're looking at displacement of the individual layers, then will that vary because the density is different of
Yeah.
the structure?
Density plays a role only if the load is dynamic. Density is different from stiffness, it's different from strength, and so on. So density has no role to play in the stress unless you are considering the gravity force as well. Okay. So in a body, so for example, I will show you an example of cataconus where you will have different properties at different layers as well as at different sections, different positions. Peripheral, central, and so on. So it doesn't matter to me that the property varies from one point to another point because the K which I am calculating will take into account that element. Say, for example, I have an element here and I have an element here. My K would take into this may be this may have one property, this may have another property. So these two are different properties and it doesn't matter to me because my K would capture these two. I am going to calculate K for every element there and then assemble by a process and so that I get the complete K, which is a matrix. That's number one. Number two, if I have a fluid, for example, you don't want to give it as IOP, you want to also model the fluid. Okay, then that is what is called fluid structure interaction problem. I'll show you some examples. So the pressure from the fluid is now applied to the surface of the solid. So the pressures are the same. And I have a method by which I calculate this velocity and pressure of the fluid, okay, by solving a set of what's called Navier-Stokes equation. And also I have this pressure to be applied at the interface to be felt by the solid. So the interfacial pressure transfer is automatically taken care of because I have an element in the liquid, I have an element in the solid, and they take care of it by proper coupling.
Thank you.
Yeah.
My background is so working as a FEA engineer in R&D departments. So while doing projects in mechanical components, for mechanical components itself, fixing a components like giving a load is very difficult because when come to the results only we know the fixing like working as a compressor, so fixing is different. So somewhere we fixed it, and giving load also we need to give the load where opposite side somewhere else. So outcome only we come to know the fixing and EBC and loading condition is different. So how do you correlate with the medical like ortho, neuro, the medical department correlate to FEA? How are you fixing that boundary condition and loading condition?
Yeah, good question. Boundary conditions are very difficult.
Okay.
Basically because most of the load transfer takes place by contact. What most companies do is they do not use contact elements.
Okay, sir.
You don't use contact elements and you start fixing at the place where contact elements are.
Yes.
So, for example, if you look at auto structures, since you're talking about components, you have to know the force flow. The first thing you do is to understand how the force flow is. So where is the action and where is the reaction? Suppose most cases in mechanical engineering, the reactions are at points which are in contact with some other component. Suppose you, I don't know what are the components, since you're talking about compressor, so let's say piston. Okay, there's a gudgeon pin, there's a connecting rod, there's a crankshaft, and so on. So the force actually comes from the piston, okay, due to, say, for example, the explosion of the gases. Then that force, if I want to calculate now what is the force that goes into the crankshaft, that force through the gudgeon pin gets transferred to the connecting rod and gets transferred to the crankshaft.
Like this, you need to take
Just 1 minute. So I have to now model, if I want to do it correctly, I have to model the contact between the gudgeon pin and the piston. Then from the gudgeon pin to connecting rod, that contact. Okay. And then from the connecting rod to the crankshaft. This is actually the force flow. But what you do in mechanical engineering in order to make the problem simple, we assume that one component is stiffer than the other component, doesn't allow it to move. And so I say that the displacement at the place where the gudgeon pin is very tough or very stiff, rather very stiff when compared to the piston. So at that 2 holes through which the gudgeon pin passes, I'll fix those points. So it is an informed decision where you look at how actually the reaction is taken, and the component which is taking my reaction, is it stiff enough not to get displaced? Then I'll fix that displacement there. If that component is also getting displaced, then I can't stop with that. I have to continue modeling that as well through special elements called contact elements.
Okay, sir. My question is neurological error. Okay, sir. Into the FEA. So how you can fix the BC condition, loading condition, that neurology?
Yeah, we'll see all the examples.
Okay, sir.
There's not one size fits all.
Okay.
So we have to look at every problem. So as we go on with the problems, you'll understand.
Okay, sir.
We'll see the example. So every problem is a different problem. So for example, I'm doing an orthopedic problem. The orthopedics boundary conditions are different. The way you are fixing it is different from, say, cornea. So every problem is different, and boundary condition requires that you understand biomechanics. It has nothing to do with finite element. It's nothing to do with finite element. It is the understanding of biomechanics, how force operates, and that is a fundamental biomechanics.
So all the components like life are fully non-linearity, sir. So you mentioned that blood flow is dynamic flow, so it come under non-linearity. So how you give the property value to the softwares, like pure stress and strain values to the software?
You don't give stress and strain value, you give that 4 baskets. So you take, for example, nonlinear elastic, then you define a model. There are parameters, C10, C20, C30, and so on. Those parameters are the ones which you give to this software. How do you give it? By doing a test on the material beforehand. Take a small piece. Say, for example, if you're doing, so our friend here is doing tire, take a small piece of rubber, find out what is the stress strain curve. Okay, then you will get a stress strain curve like this. Then you have, what as madam asked, a hyperelastic model, your model. Your model has 3 quantities, C10, C20, C30. Fit the strain energy function for this curve and then feed it into the software C10, C20, and C30.
Like
So stress and strain.
Material and tire is okay, sir. Sir, for taking small piece of tire, we take a test and we get all the values. But human body, like bloods and nerves, how you take that values?
Exactly. So there have been a number of studies already where they have characterized many parts of the body, almost all parts of it, including cornea. The problem comes when there is a disease state, when the properties change. And that's the future of medicine. You know, how actually the properties change, and because of that change, how actually the mechanical behavior varies is the problem. So this is usually done by an inverse problem, okay, by using what is called as parameter estimation. So you know the result. You already know if this were to be the result, what is the property. And then you find out the property.
Last question. So what are the software? Let me know. I'm using an Altair, Hypermesh and ANSYS and SimLabs.
Yeah, ANSYS is fine.
Okay.
Hypermesh and Abacus. We use Abacus and we have our own codes. For many of them, we write our codes, but Abacus is a good software. ANSYS is equally good. And I don't want to be quoted. I think it is a webcast. Someone is going to say, Professor is advocating Abacus because each software costs lakhs and lakhs of rupees. So I'm not advocating any software. So my simple answer is, whatever software you can buy, you can use it, please use it.
Okay, because I'm working as last 4 years in Hypermesh and Abacus, ANSYS. So I thought suddenly mechanics means medical institute will help to the Hypermesh. I was shocked. That's why.
No, Hypermesh is only for meshing.
Meshing.
Yeah, Hypermesh is a good software. We can use it for meshing.
Yes. Okay.
Right?
Okay.
Yeah, you can use Abacus, ANSYS, LS-DYNA, depending upon the problem. You can use any of them.
Thanks.
Okay, so any other question?
So, so can we understand the pathophysiology of the ocular injury after any external force? So it will come under fluid and solid interaction.
I didn't catch your injury.
To understand the pathophysiology of the
Pathophysiology?
eye ocular disease. So it will come under fluid and
No.
solid.
See, the models won't change. The properties will change. Okay. So it doesn't matter whether the fluid there's a change of the property or solid there's a property change. It's the property that changes and not the fundamental model. The model remains the same. Okay. Cornea, if there is thinning, then the geometry that changes. Right? So that's what is. Yeah. We'll break for 3 minutes or 5 minutes and then we'll shift to. Okay. We'll continue with a few examples and you can stop me anytime. We'll connect whatever we've been talking about in the first half. We'll see how we are going to apply this technique for a number of problems. In fact, for every organ, finite element has been done. So that way it's very interesting and every organ has been analyzed. We started this work, my collaborator has been Dr. K.R. Balakrishnan for the past 22 years. We've been continuously working on very interesting problems and all the problems which we have published have clinical implications. In fact, we have 3 times more material than what we have published, but we publish only if it's clinically relevant, or else we usually don't, there's not much publications. But when we published our paper in 2002, a paper on dynamic analysis of aortic valve using finite element method, in 2002, this was, in fact, a BTech work. And on fine day, Dr. Balakrishnan entered my lab and said that, can we do something on what is called finite element? I said, sure. So we published this paper, quite an involved paper at that time, on aortic valve physiology. And this paper is one of the highest. It is entered into 5 textbooks, cardiothoracic textbooks, and has resulted in changes in valve replacement procedures and so on. So we didn't expect it. And we had a very interesting result, which I'll explain. And you'll also understand why we do finite element. But what is also interesting is an editorial that was written on this paper. You can see that what he says is not, please don't misunderstand that I'm trying to boast about the paper, but I'm very impressed by this editorial. So which says that, which vets this paper, which vets the unlikely partners of structural engineering and heart surgery. By the way, this was published in Annals of Thoracic Surgery, one of the top thoracic surgery journals, which the unlikely partners of structural engineering and heart surgery is readily appreciated. It represents, in fact, nothing less than a vital component of a clinical tool of the future. This was 20 years back. That has the very real potential to change our subspecialty practice. This is the key to model's potential as a clinical tool. It will allow us to enter clinical specific, problem specific or patient specific variables and then test the various therapeutic options that are available to us. So in other words, this can become a very important tool for planning of treatment protocols. So we had seen this just now. So I'm going to take you a simple example. It's quite a simple example of plaque rupture and myocardial infarction. So I'm going to pick up one from each of these baskets. So this is static, it's a nonlinear hyperelastic problem, which is called plane strain, is the structural behavior. Don't worry about it, what it is. It is a nonlinear Ogden is the hyperelastic model, and we have a loading like this. Okay, we'll do that later. So now let's look at the problem that we are analyzing. Now that is atherosclerotic plaque, and the most important even here is this is the cap. The cap ruptures, the atherosclerotic lipid comes into contact with the blood, and there is a thrombus formation, and result is the myocardial infarction. All of you doctors, you know this. So what is that we are looking at? We are looking at plaques, producing non-flow limiting. Note that carefully. If it's flow limiting, 99% block, the guy has symptoms. We are looking at asymptomatic heart attacks and the reasons for it. This is the fundamental philosophy or the reasons to understand this work. This was done in 2004 or 5, published in British Heart Journal. Okay, the interesting point is that the plaques producing a more severe luminal diameter stenosis is not a problem. 75% of rupture takes place less than 50% stenotic. 60% of the plaque rupture tend to occur in the shoulder region of the plaque, a region of increased macrophage activity, neovascularization, and so on. Increased biomechanical stresses correlate closely with the site of plaque rupture and so on. So essentially, what is that we are doing? We are looking at the stress, and if the stress is greater than the inherent strength, then there is a fracture of the cap and there is rupture. So we modeled this. We looked at various histopathology reports, and then we ultimately modeled the plaque, ideally to understand the parameters which has an effect. So those are some of them which obtained from the actual figures. Okay, so we applied pressure now. I'm not going to explain because this is a paper by itself. The only thing I want to tell you is it's a very interesting result which some of the cardiologists know it, and they call it as law of Laplace. But many may not know this, that look at that. So the maximum stress actually reduces with higher stenosis. So if there is a block, 80% block, we usually hear 80%, 90% block. The guy escaped, there's no MI. That's also because the stresses actually drop with stenotic block. So then on the other hand, there is the strength. The strength also drops. When both of them cross, there is a failure. So this kind of work now helps us to understand that it is just not the stenotic block that is responsible for failure. It is also the amount as well as where it acts. So where the block, actually where the lipid concentrates on. So both of them combined together would give you the incident of myocardial infarction. So it's a very simple method, which is using nonlinear elastic, looking at the fluid pressure. It is a static problem and gives you an idea why there are asymptomatic heart attacks. You can also look at, say, for example, the histology sections with calcification. And there's a big question among cardiologists whether calcification stabilizes a plaque or is harmful or it neutralizes or nothing happens. So we took a number of histology sections to understand this. So, and then modeled it. So what is the answer to this question is one of the key area of the study. So that is you can see the elements there. Those are the elements. And where they join together, those are the nodes. You can now see that the properties are not a constant. The properties vary in the region. One part of the region has calcium. The other part has lipid layers. And then you have different properties in different parts. That's a lumen, endothelial layer, and so on. So now, what is that we are interested in? We are interested in if this is the calcification, what happens? If the calcification is at another side, what happens? So suppose the calcification is at a different position, what happens? And so on. So one of the interesting, so for example, you find that calcification can be at different positions. It's not necessarily at one place. So one of the interesting results that came out is that the plaque can be stabilized, or in other words, there need not be a fracture. The cap strength can be, or cap stresses are lower, or it can be an unsettling calcification, or nothing may happen. So all three are possible by using finite element, and the ensuing stress because of this calcification tells you that all three are possible, and each case is different. And if you want to evaluate calcification, then you have to do independent finite elements. So that is what this study says. It's different with the lumen shape as well. So this is a sort of gives you an overall picture of why the incidents are different. I'll not go into the mechanics of it. There's a lot of things on mechanics. I just want to tell you how finite element is done. So one of our early work, I just now said, is aortic valve. So we wanted to understand the mechanics of opening and closing because it has,
How long does it typically take?
Good question. The curve keeps dropping. What we did 20 years ago, it would have taken 5 days. Today it will be about 3 to 4 hours. But it's a very important question because we still face this problem. See, we do a lot of work on heart failure. So we want to produce a digital twin of the patient, and we want to treat him in the computer to find out which actually treatment protocol works. Now, if I do finite element, it takes a long time. I can't do this. So what we have other techniques by which we combine finite element, go into what are called lump parameter models, and then extract out some information and make models simpler so that I can get results in the next 10 minutes, 15 minutes, and so on. It's a big topic. The question you asked is very interesting because we also use synthetic data to do machine learning techniques in order to extract the information from a number of results, which I would call running it in peacetime. Then when there is a wartime, we use this synthetic data to predict the data. Because, say, I want 5,000 patient data, and I'm not interested in 90% of the patients get treated, pardon me to say this, without doctor's intervention. Doctors are interested in that 10%, 5%, 3%, 2%. So only 2% of the people will be really sick, and that's where maximum problems occur. And when we have a digital twin, I'm looking at that 2 to 5% of the people. The data availability is very small. Whatever be the hospital, whichever be the hospital, the crucial critical case data are small. So we have to create what are called synthetic data by using these kind of models. Okay, so there are a number of, it's a big topic. I would love to discuss that later, but good question. Okay, we have different strategies, but the models remain the same. So as I said, we want to understand the physiology and how actually the valve opens and closes. So that's the model. I'll show you. This is a fluid structure interaction model. So you can see how the valve opens. Bottom is the left ventricle, so the fluid goes up. So fluid and the solid are modeled, and the pressure from the fluid goes into the solid in order to open the aortic valve. That's the aortic valve, and you can see that. You can see that opening. Okay, a lot of information can be obtained with this. So it's a fluid structure interaction, shell element, Newtonian fluid, that 4 baskets. We fix the bottom because the rings are usually fixed. Okay, they don't move. And this gentleman who asked the question, good question. So we know from understanding the biomechanics where you have to fix it and so on. In fact, we have done the complete aorta and other cases. So what is that? What came out of this? Why is it that this study is interesting, and why did we do it? Now, in normal condition, the gradient that is required for this aortic valve to open is just 2 mm of mercury across. Just the difference of 2 mm would open the aortic valve. So when we say stenotic valve, this gradient keeps increasing, 10, 20, 32, and so on. Now, we wanted to understand actually a natural valve. Why would it require just 2 mm of mercury to open the gradient across? You find that the mechanics is fascinating. So this is what is called as the aortic root. So the pressure and the valves they are tricuspid valves, and they are held together by the friction between the valves. There's a friction here. So when there's a pressure on the aortic root, the root starts dilating. It starts expanding. So when it dilates, then there is a pull here, and that releases the friction here. So it becomes very easy to actually the valve to open. So it is a pull release mechanism. So why is this important? Because when there is a valve replacement surgery, then it becomes important that the root is preserved. Because if you put a stiff root, then the gradient that's required to open is high. So root sparing surgery is one way in which you can open. And if you want to have a tissue valve or whatever it is, how you are mounting, that becomes important, because if you have a rigid ring here, then you require much larger gradient across the valves. So this is important from that physiology point of view as well as the treatment point of view. That's why this has been cited in a number of cardiac surgery textbooks. Okay, this is just one valve removed just to show you another view of actually how the valve opens. So this graph explains what I said. Interestingly, the valve actually is supposed to be one-way valve. If you ask any cardiologist, he would say that the valve opens because of this gradient. The interesting point is that the valve actually starts opening even before the gradient is developed. You can see it here. That is because the pull mechanism starts opening this. Many people didn't even believe this. Fortunately for us, a Japanese group published a paper which showed what we did was correct, and then this has been accepted. We have about 200 odd citations for this paper. Okay, an entirely different topic on brain shift in neurosurgery. One of the problems of using neuronavigation system in neurosurgery is the brain shift. as soon as craniotomy is done, the whole neuronavigation system goes haywire, because the brain starts actually shifting. The shifting is because of the cerebrospinal fluid, which is responsible for the good old brain to be, you don't develop head weight. So that is going to now has a very different role here now. And also the gravity is going to act, and so the brain starts shifting as soon as a craniotomy is done. So we wanted to understand how actually the brain shift takes place, and whether again a patient-specific models can be obtained, developed, so that the craniotomy procedure can be modeled beforehand to understand the brain shift, and the failure due to neuronavigation system can be compensated. There are other ways of compensating the neuronavigation system, but one way to do is also to do a finite element. So brain is segmented, the tissue, then we look at the cerebrospinal fluid. Again, it's a fluid structure interaction problem, and a detailed fluid flow model has been created. Okay, you can see that the ventricles in the brain are all modeled, and the fluid path is modeled. And as this gentleman asked, so we have a very interesting boundary conditions here, and we took a patient brain, we modeled it, and then again it's a solid element for the solid. It's a fluid structure interaction. There is a fluid element. So we solve two equations, and we have a boundary condition with the stem of the brain fixed, and we also have a pulsatile flow of the CSF which comes out of the arterial flow. That has been modeled, and the mental model what we have used here is a hyperelastic model, and the boundary condition requires some understanding of the fundamental physiology, but nevertheless, the boundary condition basically is to fix the root of the brain stem, and then we have used an Ogden hyperelastic model, and it's ubiquitous everywhere. It is being used with a Newtonian fluid, and so on. So that is the fluid region, and that is the solid region, and that's how the boundary conditions are given. That's the boundary conditions. The most important thing is a gravity load. So you can do craniotomy, you can enter through various positions, parietal or temporal or occipital, supine position, prone position, whatever it is, and then you have a gravity load that is acting. So then if for a particular patient, it is possible to actually find out what would be the deformations as the cerebrospinal fluid starts escaping, and the pressure differences start developing between the cranial pressure and the atmospheric pressure. As soon as a craniotomy is done, it is open to the atmosphere, and when the differences of pressure starts pushing the cerebrospinal fluid, apart from that, the gravity force also acts. So the brain starts shifting. You can see that with a gravitational load, this is in mm, it can be as high as 2.57 centimeters. This has been recorded, measured as well. So, So we have for different positions and different types of entry, we can calculate actually displacement. So it's again a fluid structure interaction problem, okay, where the loadings are from the fluid as well as from the gravitational force. Okay, so this is another problem, another area where you can use finite element to understand the approach to surgery. So cornea, we have discussed a lot on this. Of an engineer's perspective of this problem is that we are looking at cornea as a laminated collagen fiber composite with a matrix of polyelectrolytes and water. So this is the key as far as we are concerned. This is the key for mechanics. Unfortunately, fortunately or unfortunately, we can't say nature is unfortunate, but it has its own ways. So it results in one of the toughest constitutive models. It is anisotropic, nonlinear elastic, anisotropic hyperelastic behavior. And it so happens that this behavior is very important. If you look at why nature had probably gone to this, is that this kind of hardening behavior is very important to maintain the curvature beyond the physiological range of IOP. So many times the material behavior or the material characterization follows the function. It does that in heart, it does that in this case, the corneal stiffness, which is governed by the anisotropic hyperelastic behavior, and that is evolved because to maintain the curvature beyond the physiological range of, say, 15 mm of mercury. The major problem in keratoconus is the collagen fiber disorganization. Okay, and you can see that that's the disorganization, and this is from a paper, and you can see how the difference between a healthy cornea and an advanced stage keratoconus. Now, the modeling is very simple. It's not at all a difficult thing. The modeling involves the material property characterization. And that is the key problem here. That connection between the pathology and the material behavior is a key area of research here. So we do not know when there is a disorganization of the collagen, how exactly the the problem with anisotropic hyperelastic is that there are a number of variables which actually define the behavior. There's not one like E value. There are number. Anisotropic means that different directions, the stiffnesses are different for the material. So I have a number of parameters which actually define the behavior, and getting to connect to the biological variations to the macro properties of constitutive model is a key factor in understanding this disease. So that's the boundary condition, quite an interesting boundary condition, because the stiffness is dictated by the boundary condition, and the boundary condition should not put stresses, and that's why this gentleman's question is important. So a lot of trial has gone into this, and a part of sclera is introduced in order that the boundary condition does not affect the results in the cornea, and that's the boundary condition. So in fact, rest of it is very simple displacement due to the effect of IOP, knuckle and fingerprint rubbing, which is a major thing for doctors on its failures, maximum tension stresses throughout the cornea. All these things are quite simple. It's not very difficult to understand. It's an excellent paper, but the key is, again, as I said, material parameters. And the property changes, the thinning, the displacement, the stresses, all of them can be calculated. One of the problems we are currently doing is a very interesting and a tough problem. So how do I now model vitrectomy? So there is, the vitreous is actually a viscoelastic material, elastic plus viscous. So essentially, that's how it looks like. And there is a cutter when you cut. What really happens is that the elastic component starts dropping. So the fluid component keeps increasing. We call viscoelasticity as solid-like and fluid-like. And when these collagens and collagen fibers and other macromolecules are intertwined, then it is more solid-like viscoelasticity. When the cutter actually starts cutting, then it becomes fluid-like. So there is a region of fluid surrounding where you have cut. Surrounding it is a region of solid viscoelastic material. And that is attached to the retina. And so as this fluid is sucked, all of you, I shouldn't explain it. Pardon me for doing this. So as you suck, the forces actually start propagating to the retina. And So there are stresses in the retina which may result in retinal detachment and so on. So we have to determine the retinal force. It's a fluid structure interaction problem. At the same time, you are also infusing fluid into the eye in order to capture or in order to retain the pressure. So this requires a very special element called coupled Eulerian Lagrangian. So I don't have time to explain that, but anyway, this is a special element. Retina is a shell, the cutter is a rigid. So you can see that sucking and the fluid getting in, sucking. It's a fluid structure interaction problem. So that is the, and you can see here, actually the retina, here, it's an ongoing work. It will take another at least 6 months to 8 months to complete it. But the model is sort of, we are zeroing on the model. You can see the retinal shell here, okay, and then the vitreous layer is here, and that's pulling the retina. One of the very interesting project which we recently doing, a PhD thesis of Sendil, who's here, is to actually understand some results. So one of the finite element can be used to get the physics when sonographers do not understand the results. Actually, the physics is really beautifully brought out by finite element. For example, this problem is for finding out the portal pressure. Portal pressure is very important in the cirrhosis of liver, and many times it is an invasive procedure. But ultrasound is now being used in order to determine the pressure, and when ultrasound is used, they inject bubbles and what is called as the subharmonic data of the ultrasound is used in order to predict the pressure. But the results are very interesting. This is a typical graph. Look at the scatter, phenomenal scatter. In fact, I don't believe these 3 points here, just like that there are 3 points, they have plotted it. But what you have to understand is that this method scatter is very high. So I wouldn't say that it is a very reliable method. And it has to be improved. If it has to be improved, then we have to understand why the scatter is there. That's the key in understanding and improving. Can I model this whole process of ultrasound itself, the acoustic wave propagation using finite element? Yes, you can model that. You can model acoustic waves in finite element. So what we did was to first understand a single bubble, one bubble, when faces the acoustic onslaught, what really happens. You would notice that this is the frequency with which you send in the acoustic signal, and you would notice that as it is received, there is another peak at that frequency of about 2.25 megahertz. This is actually the modal frequency of one bubble. And so the bubble starts actually vibrating violently at that frequency. And because of which it sends out waves which are captured by the receiver. So when it is captured by the receiver, because when I look at it in the frequency domain, the amplitude of that vibration is high, and so I capture it. So in other words, the subharmonic signals the presence of a bubble inside. And more importantly, not only does it signal the bubble, but it also, the amplitude of vibration depends upon the atmospheric pressure, that is the pressure around the bubble. So you can see that the pressure varies. You can see it here with different pressures, the amplitudes are different, and you can plot the amplitude versus pressure, and that is what you see here. Now the problem is that for a single pressure it looks a very nice some straight line graph, but why is it that there is so much of scatter? So what actually Sendil did, is to have multiple bubbles. He had put 50,000 bubbles in the region of interest. And then he makes all of them vibrate. All of them emit now acoustic waves. And these acoustic waves are captured by a numerical receiver, which we keep at the surface. Then this receiver now throws up the results. And these 50,000 bubbles are with different sizes, as is usually done in an experiment. So when you do that, you can see the scatter. It clearly shows that the scatter is because there is a number of bubble sizes and the bubbles are randomly distributed. Both of them can never give you a good result. And so the numbers are important, the sizes are important, and I can capture, you can see that both of them are very similar, this is completely numerically simulated. Okay. There may be some differences we do not know exactly the characteristics of the ultrasound probe, but we know a standard ultrasound probe. So that has been completely modeled, and you can see the difference, you can see the similarity between them, the values here, and so on. So essentially, in other words, if you don't understand a diagnostic technique, the results, it is possible to understand it, okay, especially when it's in the development stage, to use finite element to understand the results as well. Orthopedics is a huge area. I'm going to skip it. We have done a lot of work in orthopedics. So implant design has been done. You can do it using finite elements. To conclude, mathematics and medicine will define the future of medicine. Time to break the wall. Thank you very much. Okay, any further questions?
So when you look over time, when biological repair mechanisms or disease mechanisms take into place, can you model how that could potentially change the structure in the future?
Yes. So right now, if you ask me how the field should develop, okay, for this, right now we need to understand the difference or the connection rather between biology and macro properties. So, and how pathology changes the biology, and what is the connection between this and say hyperelastic parameters. Finite element doesn't need any, it's quite well developed, but it is this area that we need. And there are molecular models that are available, has not come to an extent where what are called phenomenological, what we are using is phenomenological models, sort of sophisticated curve fitting. Though based on certain laws of thermodynamics, still it is phenomenological models. This is the problem we are going to face in AI/ML as well. Because unless you know the causal effect, I won't believe any of the AI/ML results. And the causal effects comes from changes in the biological parameters. Steel metallurgy still defines the way steel works. Steel metallurgy is important. That's exactly what we are saying.
Thank you.
We have age, ethnicity, race determining this changes. How would that be replicated?
Yeah, every change, whatever be the reason, will have an effect on the results. Fortunately or unfortunately, in India we have not done a lot of work, but biomedical labs, biomechanics lab world over have characterized this, with age, ethnicity. Especially ethnicity is very, very important. I've heard doctors say this again and again. Operating in Australia is different from operating in India. I work with a lot of cardiac surgeons. Your good friend Vichit, who operated in Australia, you ask him, he says that's totally different experience when compared to what you operate in India. So this is very important. I feel a program on understanding our ethnic data on all these behavior, pathological behavior as well as the properties are very important. Without that, this would remain only a good tool. Simultaneous to this, another route should be to determine these things. We are working on certain techniques, but I would say that lot more has to be done. We just started. It's a powerful tool, shown lot of promise, but fundamental underlying science has to be understood.
I wonder if patients' histology samples, would it give you some additional cues to get more real life data than synthetic data, like in defining the finite element components?
Good question. And I hope when you reach my age, this question will be answered. Because if you can connect histology with phenomenological properties, okay, this is a huge jump. Excellent question, and that's the jump we are looking at. Can you connect structure, fundamental structure, with hyperelastic properties? We are finding it difficult even in a controlled experiments like rubber. So if you take a rubber sheet, for example, just a rubber sheet you make, the hyperelastic models are the same. You cut the rubber sheet at this end and cut the rubber sheet in this end. And if you look at the three properties, they are 10% different. Highly controlled experiments, this gives you 10% difference. So because there is small changes cause this difference. So what you asked, if someone, people have to work on this. This is very exciting. The first thing is this molecular modeling and all that, but it's not come to a stage where it can be directly used in finite element. There's been a lot of attempts, but not to the patient-specific models. But this would be very interesting.
So just one question. See, we assume that whenever we are talking about finite element, we're looking at everything from a mechanistic point of view, that everything is happening because of some physics laws. But in biology, many of the things, there are biochemical reactions which may not follow exactly the thing. So do you have anything where you can, with finite element, do some biochemical? Is there any model like that?
Anything which is defined by a differential equation can be solved with finite elements, period. If the biochemical reactions are due to diffusion laws of diffusion, okay, or other things, reactions. And if you're going to write a equation to it, I will solve it using finite element. Tomorrow you are looking at share market and you want to understand whether your shares are going to increase or not. You're going to you're going to apply Black-Scholes. I will solve it using finite element. So there's a book called Finite Element for Financial Engineering. Okay, so you can do that as well.
Yes, the information you get, is it two-dimensional or three-dimensional? And this would matter.
Which information?
From the, yeah.
Three-dimensional. Three-dimensional as well as time. So it's actually 4 dimensions. I can get information in 4 dimensions. 3 dimensions plus time. In fact, you saw that. I mean, just you can't view it, so we had put it as 2D. Actually, you saw that how the fluid actually flows with respect to time, and how actually it gets distributed X, Y, Z directions.
And in a non-homogeneous tissue,
yeah,
you would be able to get differences in...
Absolutely. Doesn't matter. So as long as I know the property, I would be able to do that. Thank you very much. Thanks for your patience. I think, sorry, we took a lot of time. Thank you.
So I'm really glad this finally happened. We have been talking about this for more than a year, but I'm glad that you finally found the time and Rajiv managed to get you here. So we're really, really happy that you could come and come with your students and speak with us. There's a lot of interest in what you said, and I'm sure with the other things starting that there are a lot of things that we can do together, and we really look forward to working with you. I was busy jotting down ideas. I'm also going to come and chew your brain sometime in the future.
Oh, it'll be a pleasure. And what Dr. Anu asked is the most important question. How do we change the properties, or how do we, like you also asked, most important thing. And I hope that will define the future, and I hope we'll be able to solve the problems. I mean, I'm not, because it's a huge topic and I don't have time. There are ideas. We are working on some of the things. I'm bringing, cross-pollinating what Dr. Srinivasan is working on tires. on exactly similar problem. We want to know whether we can bring it to biomedical and do this. I think that cross-pollination would be very helpful, and I need all the help from you to, together we can really progress. Thank you.
Absolutely. I mean, I'm sure everybody here would be more than happy to help. Thank you.
Thank you. Thank you very much.